So letting x1 to xn be i.i.d. random variables with the same mean, same variance, and skewness. In question A, we are given that we're standardizing these xj's, all of them, with the z variable. We are letting the sample mean of xz be of the sample mean of these variables respectively. And now we're going to show that x and z, z and x, sorry, have the same skewness, and the same with the standardized sample means and the x sample mean. Okay, so let's start doing showing that x and z are that they have the same skewness. So the skewness, by definition, of x, so this is just a definition, is the expectation of the random variable, its mean, divided by its variance, and then everything to the power of 3. We take an expectation of that. Okay, and this, just by definition, is gamma, right? It was given in the starting information here. Let's see what the skewness of the standardized z. Well, so I'm being a little sloppy here, which is that we should actually and technically write i's here because we're doing this for all i's. J's, sorry. Okay. So now by definition, again, what's the skewness of this zjth variable? I'm going to write mu, just going to write z here to signify that this is the expectation for z. The same should be here, expectation for the x variable. xz, like that. Okay, now we know that mu z and sigma, so this one is, just because it's standardized, is 0, and this one is 1. So we end up having expectation zj over 3 here, okay? And this is because, sorry, it's the standardized variable z is just by definition exactly what we are looking for, right? So this expression here is exactly that expression there, and hence this is, oops, is gamma. So we've shown the first part of the question at hand. Let's move on to showing the sample means, what they amount to. Okay. Call this, just answer part B here. Part B, this was just part 1. All right, so the skewness, again, of z, the sample mean of the z's, of the x's, let's see, it's just n, right? Yeah, exactly. Expectation, again, this is just by definition. The sample mean x, and the same with the variance should be the sample mean variance. Okay, and so this we need to calculate, obviously, because that information is not given. What does this mean? What is this variance? So let me just write 1, 2, and then let's do that just here. And what we know that if we recall the chapters, that it should be mu. But let me show you that. I don't like memorizing stuff. I like to, well, as much as possible, try to use intuition definitions to find out what the quantity of interest is asked for. So some mu here. Let me just make some space again. So mu of xn is the expectation over this variable, and by definition that inner term here, this one in here, is the sample mean, which is the sum over from I1 up to n for all the xi's, right? And by linearity we can take out the 1n, and inside we have now a sum of I to 1 to n xi, and this inner term, we know that they are mu, and we have n of them, so we end up then having 1 n times mu of x, and that is just mu x. Well, yeah, mu x that was defined as mu here, but I'm just trying to be extra careful to define by an index what we actually are quantifying. Okay, so let's do the variance. And the variance of this term is squared, sorry. X in, and just to be clear, I said variance where it should be standard deviation, obviously, here. So just to be clear about that. So we'll use the same trick. They have variance, and when I'm just unpacking what that variable means, xi, I1 to n, and when we take out a constant from the variance function, we square it. So we have square, and then we can, under some mild conditions, pull in the variance as we did with the expectation term. Basically, we need independence there, like the following, and we know that, or we're given that the variance is sigma squared. So now we have n sigma squared terms, and that is then n sigma squared x. Okay, so we continue ahead here. expectation of x minus mu x, and here we need to take the square root of this term, so we end up having not green, sigma squared x divided by square root of n, and that is the skewness of the sample mean. So let's, we could obviously just try to unpack this whole thing here, but we'll leave it at this, because we'll see that the skewness of the standardized version will be just this term here. So we don't have to actually show what it is, we just show that the terms are equal. Okay, so the next step is to show what the figure out the skewness of the standardized sample mean. Okay, so we have an index here. Yes, we have like that. And then by definition, again, the skewness is the expectation, z n minus mu, and now it's the right expectation, sorry, the right mean there should be mu z of that sample standardized mean. Here we have the same thing, and here we go. So we now have to do the same operation. We have to figure out what mu is and what sigma is for these terms. Now, for mu, because it's standardized, we know that it should be 0. So let me just write this as 0 here. However, for the variance, it's not necessarily 1. So let's go ahead and calculate what that term is. Do it in green again. Oh, let's do it in blue. So this term, and I see that I've mistyped. It's not x, it should be z. Okay, so that we do here. The same thing we do then the variance, squared, the variance of Zn is just by definition what I wrote, and then we again by definition unpack the inner term, which is 1n, the sum of I1 over n zi, and by the way, I just realized I wrote we have i's and j's, but let's stick with i's. All right, so same operation here, squared. We do the sum, the variance of zi, I1 to n, and that we know what it is, this variance term. That variance term is 1. And so, and we have n of those ones, so we have 1n squared, n times 1, we end up having 1 over n. Okay. let's then keep on pushing this expression here. So we have minus 0, but divided by 1 divided by n, and that term we well, it should be squared. Yeah, exactly, it should be the square root of that, so it's 1 divided by square root n 3, like so. Okay, so this looks a little messy right now, but we are actually pretty much, so let me just do an equality, but I'll continue down here. So this, just put a star here, star here. Here next we can use just again the definition of what this sample, standardized sample variable is, and do that expectation. That is 1n, the sum over z i's i1 to n, and then we have I'm just going to pull out this term, which is zn here, like this, divided by 3. Okay, this looks right. And then we do another thing, because remember, what are we trying to do? We're trying to push these terms, yeah, skewness, and translate it down to x's, and then into the sample mean of those x's, right? So we're keeping on translating from z bar to z's to x, and eventually to x bar. Okay, so let's do that. So what we have now, we have, well, all the z's are the standardized x's. So let's just do that. So we have xi minus mu. I'm just going to use mu here, which is mu x, and the same with that, like so. This I have there, Zn. We could pull out the 3 and the root n. Let's just keep it there for a moment. All right. Now here next, how do we move? Well, what we have here now is the sample. This is the sample mean, correct? Right, so I'm going to expectation 1 over n. What we have here is there's actually a little well, not a trick, but I just want to remind us of a key thing. So let's look at the term here, which is well, that's the standardized version. We can pull this exactly. So we need to in order to move to x bar, we need to get rid of this and that. Okay, get rid, basically just pull it out from that term there. Okay, so let's do so. And going to write one equality here. I'm going to show you how it comes that it is true. So expectation. Now we have, I'm pulling out the sigma here. Okay, so it's now sigma root n expectation like that. Okay, so what did I just do there? Well, pulling out the sigma is not a problem, right? We're just multiplying everything with 1 divided by sigma, so you can pull it out there. But this part here, this little part here, can seem to be a little mysterious. So let me unpack it. So what do we have? We have, what we're left with is, here is 1 divided by n. So 1, let me use another color. 1 divided by n, the sum of xi minus mu I from 1 to n. All right, so what does this mean? Well, if we unroll the sum, what we have x1 minus mu plus x2 minus mu, and so on up to n. Xn minus mu. Now we have then n mu's, right? So we have 1 n and then x1 plus x2, so on up to xn. We have n minus 1 minus n mu's, as I just said. Okay, and then 1n, we can now just open up that parentheses and, well, basically pull out this mu term. So now we have, going back to the summation notation, 1 over n, and we have minus n and mu, like this. So what happened? Well, pulled out the minus n mu, but we have to multiply by 1n, which is what we're doing here. And now we have the sum, and this whole thing now is xi i1n minus mu. But this term here is now xn, x bar, which is exactly what we have here. Okay, so it was a little manipulation that that now has brought us to the x bar. We are now basically, essentially done, because we have shown that this term here is exactly that term there. Okay, and just to be clear that these mu's here, this one is for mu x, and that is sigma x as well. Okay, so now we've shown that that second part of the first question, a little bit convoluted and admittedly a little complicated, but nevertheless we've done that one. So let's move on to the next part, which is B. And now we're going to show that the skewness of the sample mean is exactly gamma divided by square root of n, and we can use this fact that if two variables, random variables, are independent, we can basically unpack their factorize their expectations in the following way. All right, so let's head into that question and show what that skewness is. Okay. Let me just check one last thing here. Right. Okay. So we want to now actually determine what the skewness is, and let's, for the sake of simplicity, work with the skewness of the standardized version, which is a little easier to work with. Okay, so we're not losing any generality by doing this maneuver, but it'll be a little easier to work with. Okay, so skewness of the standardized version is now, let me just move in this direction. Well, let's just do this, which is now by definition the expectation of z, and we know that the mean is 0, so I'm not going to write it out here to the left. We know by the previous question that the standard deviation is 1 divided by square root of n. And so here we're going to then just pull out the n term, and so we have to, when doing that, we have to put it to the power of 3. So we end up having n3 to expectation of z n, like this. Okay, and so let's just again use the definition of the standardized sample mean of this, which is then 1n sum from I to 1 to n zi, like that. And right, we're dividing by n. Yes, exactly. I was a little confused there. Like so. Okay, so this is interesting. Now we're asked to actually calculate what the skewness is. So we do have to unpack, basically factorize out this whole thing to the power of 3, and doing that we can use the hint, which will help us to make this calculation a little easier. It looks a little messy, but let's head to it. So basically, just to make this a little clearer for us, let me do the following. So this term, let me calculate here, which is that, well, what is it? Let me just also we're pulling out the 1 divided by n just to make it easier here. Okay, so let me just focus on the z terms. So then we have z1 up to plus zn3. Okay, so when we multiply out this, we will end up with having terms like zi3s. We will also have terms that look like that, where we're powering up to 2 And then we'll have 6 x1, x2, x3s. I mean, you can see this by starting to multiply out a bunch of these, and you'll see that we end up with these pure terms and these mixed. Well, now I wrote x's. Okay, sorry about that. Let me z, and it should be. Let me start from the beginning. Sorry about this. Getting a little convoluted. 3z to the power of 2, z2, 6, z1, z2, and so on and so forth. I mean, these are the terms that you get when you start multiplying this out, and you'll see, basically using binomial theorem, you'll see that you have many of those power terms. Okay, but what does this say to us? How does this actually work out? All right, so what will happen here is that we can now, by doing it, we'll end up having a bunch of linear combinations that we can then use the expectation to unpack it. And the benefit is that we can then we know exactly what those expectation terms are. Okay, so let me just show what will happen is that we'll have. Let me actually just write out. So we have z1 and then up to zn, so pluses here, 3, and then we'll have the same thing, 3 z2 1 z1 2, sorry, like that, and we'll have a bunch of those terms. And then we'll have plus 6, that should be z3 here, z1, z2, z3. Okay, and now when we do the expectation over this, remember, because we have the expectation term here, and because these are independent, so for example now, this term, when we do expectation over 6, we can pull the 6 out, z1, z2, z3. This by independence, we can do the following. z2, expectation z3. Now, what's the point of doing this? Well, these are all zeros. That's the beauty of it. All of these are zeros. The same will happen here. So what we end up with is a bunch of terms, these independent terms, well, up to here. They are the ones that amount to the skewness of the of these variables. Sorry, I'm watching my notes simultaneously, so I get a little slower here. So what will now happen then is that we get n just looking at my notes there. Yeah, so we have n gammas. That's the thing. N gammas, because those are n. And then divided by n3 not m, but n, 3, 2, like so. I'm just checking whether, right, yeah, 3, 2, and then we end up with gamma n half, which is the same thing as gamma squared n. Okay, and that concludes the B part. So let's do the last one, which is, here we are asked, what does the result of B say about the distribution of the sample mean when n is large? Well, this one, well, we can see that by gathering more samples, so as n goes to infinity, well then the skewness of xn will tend towards, I mean, not equal, but tends towards 0, right? Because you have a large number here divided by gamma. So that is what will happen as we gather more samples. We get a more normally distributed distribution. Okay, so that concludes this exercise.